In this video, we're going to look at the convergence of a recursive sequence. And the question here is to show that a sequence an defined recursively as a1 equals 1, that's the first term, an plus 1 is equal to root of 2 plus an. And we want to prove that this is an increasing sequence and bounded above by 2, and also we want to find a limit as n goes to infinity of an. So let's compute a few terms of this sequence. We have a1 is equal to 1, that's the first term. a2 is equal to square root of 2 plus a1. And that gives us square root of 2 plus 1 is equal to root 3. And if we decimalize that, we get 1.73 approximately. a3 is equal to root of 2 plus a2. Now plug in a2, so we get root of 2 plus a2, which is root 3. And if we decimalize this, we get approximately 1.93. And let's look at a4. a4 is equal to root of 2 plus a3. That's equal to square root of 2 plus a3, which is root of 2 plus root 3. Put this all into a calculator, and we get approximately 1.98. So we can kind of see from the first few terms, the first 4 terms of this sequence, that this sequence is increasing because we have a1 is equal to 1, a2 is 1.73, a3 is 1.93, a4 is 1.98, and it seems to be also bounded above by 2. But we need to formally verify our intuition by applying mathematical induction. Alright, so let's start by proving that this sequence is increasing. And to do that, we have to show that an plus 1 is larger than an. For n larger or equal to 1. Let's start with a1. a1 is equal to 1. a2 is equal to root 3. So definitely a2 is larger than a1 because root 3 is larger than 1. So this condition, an plus 1 larger than an, holds for n equals 1. Now let's assume that an plus 1 larger than an, this condition is true for n equals k. That is, ak plus 1 larger than ak. Now let's look at ak plus 1. ak plus 1 is equal to square root of 2 plus ak. But this is less than root of 2 plus ak plus 1. Why is that? That's because ak, by our assumption, ak is less than ak plus 1. We're assuming that this result is true for n equals k. That means ak plus 1, the successive term, is bigger than the previous term. But if we look at this very closely, this is actually ak plus 2. This is the term ak plus 2. We have proven that ak plus 1 is less than ak plus 2. Or equivalently, we can write this as ak plus 2 larger than ak plus 1 to show that this is an increasing sequence, or ak plus 1 is larger than ak plus 1. So what we have shown is that an plus 1 is larger than an is true for n equals k plus 1. But we also know that an plus 1, by assumption, an plus 1 is larger than an, is true for n equals k. So by mathematical induction, an plus 1 is larger than an for all n. Now let's review the process. First, you find that this is true for n equals 1. So for n equals 1, an plus 1 is larger than an. We have an increasing sequence. Then we assume that this result is true for n equals k, And we prove that it holds for the next one, for n equals k plus 1. And we prove that ak plus 2 is larger than ak plus 1. That means this result, an plus 1 is larger than an, is true for n equals k plus 1. By assumption, it's true for n equals k. And in the beginning, we proved that it holds for n equals 1. That's true for, let me write this, true for n equals 1. So by mathematical induction, an plus 1 is larger than an for all n. So we have proven the first half of the question. Now we need to verify. So need to verify that the sequence an is bounded above by m equals 2. Bounded above by m equals 2. That is, we want to prove that an is less than 2 for all n larger or equal to 1. All right, we've already proven that an is increasing. So in the first part, we applied induction and we proved that an is an increasing sequence. It's monotonically increasing. And if it is increasing, it must have a lower bound. That means an is larger or equal to a1 equals 1, the first term, for all n. And so we have a lower bound, so an has a lower bound, L equals 1. Let's apply induction to prove that an has an upper bound, m equals 2. So we would like to prove that an is less than 2 for all n. This is what we like to prove, so prove by induction. Now, let's go back to our recursive relationship. An plus 1 is equal to root of 2 plus an. And we know a1 equals 1, and n is larger or equal to 1. So let's start with a1. Well, a1 is less than 2 because 1 is less than 2. So that means this result, an is less than 2, is true for n equals 1. So an is less than 2 is true for n equals 1. Let's assume that an is less than 2 is true for n equals k. And then we must show that it's also true for n equals k plus 1. So that means that ak, because an is less than 2, so n equals k, ak is less than 2. We're assuming that n equals k. So let's look at our recursive relationship. Ak plus 1 is equal to root of 2 plus ak. This is less than root of 2 plus, but ak is less than 2, so I can just put 2 here. We get root of 4, which is equal to 2. That means ak plus 1 is less than 2. So an less than 2 also holds for n equals k plus 1. So let's review. We show that an is less than 2 is true. So when we say holds, it's the same thing as saying true. So an is less than 2 is true for, we proved it's true for n equals 1, and we assumed it's true for n equals k. And then we also proved that an is less than 2 is true for n equals k plus 1. So by induction, an is less than 2 for all n. That means it has an upper bound. The upper bound is m equals 2. So m equals 2 is an upper bound for the sequence. So it's upper bound for the sequence an. And we proved that by induction. Now, let's review what we've done. We've proven that the sequence an The first half proved by induction that this sequence is monotonically increasing. Monotonically increasing. The second half, we proved that this sequence is bounded above by 2. It has an upper bound and is bounded above by 2. So therefore the sequence AN, because it is monotonically increasing and bounded, it must converge. So AN must converge to a limit. Let's call that P. Converge to a limit P. So basically we're using the theorem that a bounded monotonic sequence has to converge. But the theorem doesn't tell us what the converging limit is. We have to find that. So what is the converging limit P? Well, P is defined in this case as a limit as n goes to infinity of AN. And we know this limit exists. Let's use the recurrence relationship to find P. The recurrence relationship is AN plus 1 is equal to root of 2 plus AN. And our starting point, the first term, A1 is equal to 1. Now, key concept. When AN approaches P as n goes to infinity, AN plus 1 also approaches P because n plus 1 is also going to approach infinity. So the limit of AN as n goes to infinity is equal to P, but also the limit as n goes to infinity of AN plus 1 of the next term is also P. So at infinity, the limit of the sequence term is just P. All right, so now we have limit as n goes to infinity of AN plus 1 is equal to limit as n goes to infinity of square root of 2 plus AN. Now let's bring the limit inside the square root, so we get root of limit as n goes to infinity of 2 plus AN. Now, the limit of AN plus 1, that's just going to be P. This is equal to root of 2 plus, and limit of AN as n goes to infinity is also P. Now, square both sides, do some algebra, and solve for P. P squared is equal to 2 plus P. Bring it all to one side and factorize this quadratic function. P squared minus P minus 2 is equal to 0. Factorizing this, we get P minus 2 times P plus 1 is equal to 0. Solving for P equals 2, P equals negative 1. We're going to reject P equals negative 1. Why is that? Because we know that AN is larger or equal to 1 because L equals 1 is a lower bound for AN. Lower bound for, let me write that better, for the sequence AN. So we accept P equals 2. The sequence AN, this sequence, converges to 2. It has a converging limit of 2, converges to 2 as n goes to infinity, and this is in agreement with our prediction, with our intuition, that this is a convergent sequence and it converges to 2. All right, thanks.